Hello, everyone. I'm Sean Clark, the Associate Director of the MTV, and I want to welcome you back for week 6 of our Nuclear Engineering Summer School. Today, we have a guest lecturer, Dr. Jorgen Randrup, who is a senior physicist in nuclear theory at Lawrence Berkeley National Lab. His research is on theoretical nuclear structure and heavy ion collisions at various energies, from just above the Coulomb barrier all the way up to the relativistic regime. In recent years, his interest has been in fission, and particularly with focus on nuclear shape evolution. So Jorgen, the floor is yours.
Yeah, thank you very much. Thank you for inviting me to be a kind of a guest lecturer here at your nuclear engineering summer school. As you mentioned, I'm a theoretical nuclear physicist. So I hope I can manage to communicate some of what I consider the important physics that comes up in nuclear fission. And you will have an opportunity to ask questions afterwards, preferably. I have a lot of things, so I will jump right into it. First of all, what is, let's see here, I can't get anything to work. Here goes. What is fission? You'll probably know that. A heavy element, typically an actinide nucleus, somehow or other splits into two fragments. That is a very spectacular phenomenon, and it involves a lot of physics, various ends. Before, though, I can get specifically to fission, I need to remind you of some of basic, more general nuclear physics features that are particularly relevant and helpful when we try to understand fission. So first, and this will be, for many of you, maybe a new word to learn, nuclei are leptodermous. This means they have a thin skin, as many of us, but what does that mean? If you have a microscopic model of the nucleus, the basic thing is the nucleon-nucleon interaction, and it is mediated by the exchange of mesons, is our current understanding. So as you come in from a big distance, let me ask, can you see the cursor? Is the cursor visible? Sean, is the cursor visible?
Yes, we can see that.
So as you come in from a large distance, the lightest meson comes into play first, that's the pion. It gives an attractive interaction. And then as you get closer and closer, it becomes more and more complicated, and the interaction turns repulsive. So you can see there is an optimal separation between the nucleons. And therefore, when you add more and more nucleons to a nucleus, it just simply gets bigger and bigger. It sounds maybe trivial. Here is a sketch of that. It just gets bigger and bigger, and the interior doesn't change. You can see here's a calculation of the density profile. It's the same density inside, what we call nuclear matter density. And then you have a surface profile that is pretty much the same for small nuclei and big nuclei. So nuclear matter saturates people, so you get the same density all the time, and it's fairly incompressible because of this very strong repulsion. And then they are leptodermous. They have a thin, relatively thin surface region. Now, this is not as trivial as it may sound, because if you compare with atoms, it's not like that at all. The more electrons you pile, or I should say, the higher you go up in the periodic table, the atoms stay the same size, because the larger the charge, the more it sucks in the electrons. So the last electron, it just sees one charge, essentially, the big Z being shielded by all the other electrons. So that's why you can have so much interest in chemistry and so on. But for nuclei, it's more like sort of normal pieces of stuff we have around. The more you put on the pile, the bigger the pile gets. And this then immediately means that the nucleus has a shape. This is the very important concept in fission. You can draw the surface like this, and then you know already what it means, that you have a clump of nuclear matter inside, and then you have this standard surface profile all around. So that's the first concept. Nuclei are leptodermous, and therefore they have a shape. And therefore it becomes important from the theoretical point of view to think about shapes first. You need shapes to describe fission. And there have been many attempts to develop shape parameterizations that are suitable, and it's not as easy as it may sound. You probably know for small deformations, you can do some Legendre expansions and whatnot, but you have to go from one nucleus to two nuclei, and then it becomes much more difficult to figure out what to do. There are many parameterizations. Most of them are not completely adequate for fission. The one I will mention is invented already 50 years ago or more. It's called the three quadratic surface shape family. It is good for actually symmetric shapes, and it says you simply divide the shape into three sections: a left shape, a right, and a middle. And on the left, you have an ellipse. On the right, you have an ellipse like this, and then you have a hyperbola in between. So that is geometrically very simple, and that you get then five shape degrees of freedom. So your shape space is not just one dimensional as here, but it is 5-dimensional. And you need all five. So you need the elongation, of course, overall elongation of the system, the kind of quadrupole moment. You need to find out how much the shape is indented as you approach scission. Here's the neck radius, thing that's called A3 up here. Then what is special about this parameterization is that it allows each fragment to be deformed. This is, of course, very important in fission because some fragments like to be spherical, others like to be deformed, and many parameterizations don't have that flexibility. So then the results are obviously not so great. And then finally, the mass asymmetry. You can see here the right one is bigger than the left one. This is what nature prefers often. So these are all important, these five. You must have them all. Maybe you need even more, as we will see. So let me just show over here an actual calculation based on some microscopic quantum theory of a time evolution of a plutonium from a saddle down towards scission. And there is no condition of shape here. It just follows from the nuclear interaction that I showed. And you can see how the nucleus really organizes itself as I drew a constant inside and a thin surface profile all around. And it looks kind of plausible that this kind of shape family over here could reproduce shapes like. Okay, next basic feature. Nuclei are mesoscopic. This means they are not too small and not too large. So therefore they have both macroscopic and microscopic features. This is also important in fission. So you can think of the nucleus as simply a drop of fluid. You have heard this before. The fluid is, as I mentioned, fairly incompressible. And contrary to normal water drops, it is electrically charged. And if you were to put charge on a normal drop, all the charge would go to the surface so they can get away from each other. That doesn't work in the nucleus because the charge sits on the protons. The protons, they don't go anywhere. They sit where they sit. So you have a uniformly charged, incompressible fluid. And then you can already understand a lot about fission. Think about how the potential energy changes when you go through a sequence of shapes, like from a single nucleus to a kind of fission process. There are two contributions to the energy for such a system. One is the surface energy. When you have a drop, you have a surface tension, and it's the surface tension that keeps a normal drop spherical because it costs energy. It's not so good for the nucleons to sit in the surface. They're not so well bound. So as you deform the nucleus, the surface area goes up, the surface energy goes up. Of course, there's a limit. At the end, you can't go up anymore once you have split. At the same time, you move the protons further and further apart on the average, so the cooling energy goes down. So you have this competition between the surface energy and the cooling energy. In the beginning, the surface energy goes up twice as fast as the cooling energy, but in the end, the cooling energy wins. So the total combined macroscopic energy goes up and goes down. So you have a minimum here. This is what holds normal nuclei together. But there's also a top here, a barrier, so-called fission barrier. And if you can get beyond that, it goes down. This already explains why heavy nuclei, or any nucleus perhaps, or at least many nuclei would like to fission. Now, the microscopic features. The nucleus is not a drop when you look inside. It has nucleates inside and they move around, not like water molecules that run into each other all the time because the nucleons are fermions. So they hardly see each other, they move around independently in a common mean field. So there's a single particle Hamiltonian, there's a Schrödinger equation, you can solve for the wave function, you can find the energy levels of these nucleons and the orbitals they go in. You have probably learned all of this already, but this is important in fission. So now the shape dependence, then the shape changes, the shape dependence of these single particle levels is important because they modify this internal structure modifies the macroscopic energy. The actual energy is not so smooth because as you change the shape, these orbitals fits more or less better into the shape. So there are some little undulations on top of this. And even though they're small effects, they determine finally the outcome of fission. So here is sometimes you have a uniform level spectrum, or ideally, if you had that, this would give you the macroscopic curve, but sometimes you have gaps around the further surface, sometimes you have bunching. So you can calculate this, you take the shape, you smoothen it out to get a potential, you take your single particle Schrödinger equation and calculate the energy levels. And then you see how they depend on the shape. This was first done by Nilsson, therefore they are called Nilsson diagrams. And you see that for spherical shapes, you have these tremendous bunchings, you have big gaps in between here, 50 particle number, 82, and so on. And then as you start to change the shape, some orbitals fit better into the elongated shapes, the energy go down, others fit worse, the energy goes up. So it becomes very complicated, but then at some deformations, there can be other new gaps. And such nuclei I would prefer them to be deformed instead, and so on. You have probably learned all of this. So to calculate the effects is a little bit technical. I'll go over it quickly. You need to calculate the so-called shell correction. The idea is just that the actual level spectrum is irregular, as you saw. Then you calculate that, but then you can smoothen it out and get a smooth level spectrum. And then you just simply integrate one, integrate the other, and take the difference. And that is according to some basic theorem for fermions, for condensed matter, and so on. That tells you the modification of the macroscopic energy due to the internal structure. So this is called the Strutinsky shell correction method. So it's very simple and very powerful. And you need to do a similar thing for the pairing. The pairing interaction in nuclei is also important, and it also depends on the precise level sequence. So again, you do a difference between the actual level structure and the smoothed out level spectrum. So then let us see what you get. So here is the result. Here is the macroscopic curve I drew before, calculated with some surface energy, Coulomb energy, and so on. And then you have the shell and pairing corrections with the Strutinsky method and the BCS method, and it goes up and down. So you see a typical actinide nucleus doesn't like to be spherical, it likes to be deformed. There's a first minimum, the ground state. Then it goes up, there's a first barrier, then there's a second class of states here, they're called isomeric states in the second minimum, and then comes the second barrier here. So this is typical how an actinide fission barrier looks, but this is just drawn as a function of, symmetric split. If you now go into multi-dimensional shape space to see what happens, you find out that down here, for the more compact shapes, the nucleus prefers indeed to be symmetric. But up here at the second barrier, it starts to prefer to be asymmetric. So the actual barrier is not as high. You can go around the barrier by becoming asymmetric. And I will get back to that. So let me just see how this works, or show you how this works. If you want now to calculate nuclear masses by this method, you calculate the macroscopic energy with this liquid drop expression. You calculate the microscopic corrections. You have this as a function of shape, and you look for the minimum, as we saw before. And then you can see how, if you take the data, you have subtracted here already the smooth behavior just to be able to see it better. So the measured masses throughout the entire nuclear chart go like this. They have a lot of structure, and the calculated ones look very similar. And the difference you can see is really remarkably small. This shows that this kind of method works fairly well, and it works much better than trying to calculate the energy sort of by brute force from microscopic forces, because that requires very high accuracy and so on. It doesn't work very well. So this is the best method for calculating the potential energy as a function of shape. So this is the yeah, good to keep in mind. It's what is being used. That's something happening. Okay, finally then, so this, now we are done with the static nuclear properties. Now we can finally go to fission. So something happens in time in fission. And the third basic feature of nuclei that is important is the fact that nuclei are amnesiacs. They have a short memory. What does it mean? Well, it came up already back in the 30s when people could shoot neutrons on nuclei, and Niels Bohr illustrated it in this nice way. Here is the one neutron coming in, and here are the other nucleons inside the potential. This was before people realized that the nucleons don't actually see each other. So, but never mind, the idea is the same. The nucleon comes in, and very quickly it shares its energy with the other nucleons. So what that means is that something like the shape evolution in fission, when the shape changes, you disturb the internal motion of the nucleus, but they very quickly reorganize themselves into new equilibrium. So the microscopic relaxation time is much shorter than the characteristic time associated with a macroscopic shape evolution, which means that in fission, you can pretty much think of a shape evolving, and all the time the internal system is in whatever, in the appropriate equilibrium. This is simplifies things. There's no memory time to worry about. Niels Bohr, when fission was discovered 3 years later, he took it up again and said it's like a sequential. First we agitate the nucleus, and then it quickly equilibrates, and then months later something happens. For example, in those early days, evaporation of a neutron or fission. So we have this kind of sequential character. Let us now then see what the stages of nuclear fission are. And I would say here, this is induced nuclear fission I'm talking about. Not so what I have to say also applies to spontaneous fission, but I will focus here on induced fission. So you have a target nucleus, uranium-235 or something, and you shoot something on it, typically a thermal neutron. And then according to what I just said, it very quickly becomes a compound nucleus. It equilibrates at higher energies. There can be some knockout of some pre-equilibrium processes, and you all the time compete with evaporation, but the compound nucleus finally then fissions. And this is the essence of fission, that you go from one nucleus to two nuclei. In some complicated way, the shape evolves. I will get back to that in some detail. Then you come to scission. This is where the two fragments that are formed lose contact. Everything is then determined. They move apart due to the mutual Coulomb repulsion, and they are rotating and they are excited, and so on. You have then the primary fragments, and now fission is over. But the physics is not over, because these fragments, they have a further fate, and they go through a long sequence of decays. First, the neutrons, they are usually sufficiently excited to emit a couple of neutrons, one or two or something, and then in increasing competition with also electromagnetic radiation. Finally, you come down to the prompt product nucleus, the ground state, or perhaps an isomeric state. From there, the time scale comes longer. Now the weak interaction comes into play, and you have a bunch of beta delayed processes until, until you could finally reach the beta stability line. So yeah, these are basically all the stages. I will concentrate, as I said, mostly on this, from the physics point of view, most interesting issue. How does it happen that the nucleus can changes like this? Now, let me first, this is a strange phenomenon, and it was therefore hard for people to believe the data when it was first discovered. It was, let us say, officially discovered by Otto Hahn, who chemically determined that barium comes out when you have agitated uranium with a thermal neutron. Fermi had already a few years earlier done the same thing, but he concluded falsely that he had made trans-uranium elements instead. And he got the Nobel Prize for that, even though it was completely wrong. Anyway, it was Lisa Meitner here, his assistant. She was the theorist who was yes, a theorist. She was also Jewish. She had to run off to Copenhagen, and Niels Bohr sent her to Stockholm. And while she was there, she met at Christmas vacation with her nephew here, who was a postdoc in Copenhagen, and they figured out what was going on. They thought about it a little bit like I have drawn for you. And if somehow you come in with this neutron, they thought you can put the nucleus into vibrations. And maybe if these vibrations are strong enough, it can vibrate over the barrier, and then the nucleus will split. And if it does, then you get a tremendous energy release, a couple of 100 MeV. So, and she got an element named after her for this discovery. And Niels Bohr, he immediately said that we have been fools because this is so obvious. We should have seen it before. That's easy to say afterwards. Now, let us then try to model fission. So we want to have the shape go from a single nucleus down to scission. And it is a little bit actually quite difficult. There's one particular feature of this kind of problem that is a big challenge to theory. And that is that you start from a relatively simple system, a compound nucleus. But you could do so many different things that you can't just solve a normal equation of motion where you have one initial condition and one final state, because you get so many things. Let me illustrate this, because this is an important point. Here's the initial compound nucleus, and it can split in many different ways into many different kinds of fragments. And for each one of them, what's going on here? I don't know if you see what I see, but I see the strangest things here.
We see like a green thing with a red band.
Yeah, there's something wrong here. Well, I don't know what's, but anyway, these are the nuclei here, and it shows that they rotate. So they can rotate in many different ways. This one up here shows that they can also move in different ways. Some of them move fast and some of them move slow. They get different kinds of excitation. So this is, I don't know what happens now. Maybe I'll take it down and start it over. Let me just see here. Let me try this one again. Maybe that didn't help here. I don't know. It worked before. Anyway, this is just illustrative, that there are many different things that can happen. You get different velocities of the fragments, you get different angular momenta, you get different excitation energies, and not only sort of in one direction, you could go in another direction. So the whole point of this is to say that you have one initial nucleus, so to speak, but you can get so many different kinds of outcomes that you can't do it in a normal sort of deterministic way. And I have coined a motto for this. Some of it sounds a little familiar. It means out, this is Latin, ex uno plurus. This means out of one kind of system, you get many different kinds of things. How can you treat this theoretically? It's difficult for the normal quantum mechanical treatments to do this. Here is again the, I don't know what's going on. I think maybe I'll try to check down the thing and start it again. I'll just do that quickly. And then let's see here, start again. That helped. Okay. See, now it works, huh?
And Jorgen, can you reshare your screen?
Oh, sorry. Let's see if I can do that. Ugh. Well, how do I do that then?
Green button at the center, bottom center.
Yeah, but there is no green button at the center.
Oh, but you have to press on Zoom.
So let me share first. Now I share. All right. Okay, very good, very good. And now it is probably this one here.
Yep.
Is it? And then I do this. Yeah, sorry about this. Okay, that looks better.
Yeah, much better, thank you.
Yes, I don't know why it didn't work, but anyway, this is I spent too much time on this, but it is important that you start from one shape and then you can get so many different ones. How to deal with this? An efficient approach is to think of this evolution as a diffusion process. So not a deterministic process, but at each time you have choices and you choose between them. Again, I can illustrate. So you have a shape and there are many similar shapes you can change to. You choose one, maybe this one over here. You go to that one. Then again, you have neighbors. You choose one, you go here. And this way you get a specific shape sequence. And then you do this many times. Then you get a whole ensemble of possible evolutions. This is a very efficient way to deal with such a problem. But this is very difficult for the quantum mechanical treatments to do. This is kind of a classical transport thing. The good thing is that the shape is more or less a classical variable. So it works rather well. This was already thought about right after fission was discovered by Bohr and Wheeler. Here is from the original paper. They draw the potential energy surface here. And they say that nuclear fission, it is the result of some kind of shape diffusion. You start here around the ground state minimum. There is a barrier. Sooner or later, you get over the barrier. So the idea is old, but to actually get it to work requires better potentials than what is sketched here that has shell effects and all of this. So what was fortunate was that for some other purposes, Peter Müller had tabulated the potentials on a huge lattice of shapes, more than 5 million different shapes for a nucleus. And then he had done it for more than 5,000 nuclei that I try to indicate here. So this is a very useful database if you wanted how to do diffusion of the shape. He used this information to find where the minimum is to get the ground state, to find where the other minimum is for the isomeric states, to see what shapes those states have, and also to look for fission barriers. But he wasn't thinking of fission, and it's as such. And in fission, you have to go out to even longer shapes. So the table has now been expanded by another million or so, so you can go out to, and maybe that's not even enough. So anyway, this, using this very elaborate landscape of shapes makes it possible to do such shape diffusion. And this turns out to be rather powerful. So here is again schematic. We have now potential in 5 dimensions with the shell corrections and so on. Here is how it looked when Peter was making his PhD 50 years ago. Here's uranium. Uranium. The first minimum is here. The first saddle, this one up here, is here. The second minimum is here. And then, as I mentioned, the second barrier, if you go symmetric, is pretty high. But if you go asymmetric, you can go this way, or the other opposite asymmetry, you go this way. So the idea is now to make a diffusion through here and see what you get. And let me first, you have to say that you have, of course, to say something about how you decide about your steps. And it is probably a reasonable thing to think that phase space plays a big, here we are again. I can't believe it. And I don't have time to go through this procedure again. When you have a given shape, you have a certain excitation energy, right? There's a total energy, there's the potential energy. So the nucleus is colder when you are on the barrier. It is warmer when you are near the minimum. So there's a lot of level density here, not so much here. And this guides how the diffusion goes. So the level density depends not only on the excitation energy, it also depends on the shape, because you know you have these structures in the level spectrum with gaps and so on. So the shape and the excitation both matter. If you use the simple Fermi level gas level density, then it doesn't care about the shape, and we will see the importance of that. So here, let's see if I can get. Okay, here's a modern version of the potential energy. The secondary minimum is here, the asymmetric saddle is here, the valley is here, and so on. The shapes are indicated here. And you then go, you go forward or not according to the level density, according to prescription invented by Metropolis. And the idea is then you start here in the ground, this is start the secondary minimum here, and you then walk around, get over the barrier, and then down the valley, come out over here. Then you can read off what the split is, and you can simply bin that, and you can get a mass distribution. So I will go a little fast here. These are the very first results. You'll see that it works reasonably well. Uranium, plutonium, uranium-234 here. There's two comments I want to make. The actual data is for charge distributions, and they go up and down due to odd-even effects. The calculation doesn't have that. This calculation does not have that in, so it doesn't have up-down. Modern ones do have that, and you get this up-down thing also. Secondly, uranium-234 here is the same nucleus, but at different excitations. Works fine for the low excitation, thermal neutrons. Higher excitation, you can see the calculation doesn't fill in as much as it should. And this is because the energy dependence is not taken into account properly. The level density is not taken into account properly. This has now been done, and we can check how well it works. This doesn't work well, but the calculation works well. Let me just skip over. There's data and there's a calculation. The data are the points of calculation. There are 70 cases here. This one is the one I just showed for uranium-234. You can see it has now been fixed, that it works. And then compare with all these different mass distributions. I go through quickly. Well, what you're supposed to see here is that it works reasonably well. And you can then, so tentatively, the fragment mass and charge distributions we can calculate fairly well and understand them as just a result of this diffusive shape evolution on the potential energy surface. But it's important to have a good shape parameterization, you know, so that the nuclei can become asymmetric, for example, and so on. And this in turn relies on the potential energy surfaces having the shell effects and all of that correct. Now, one application is to try to calculate mass distributions for many, many nuclei and just see if they split symmetrically or asymmetrically. Here is 1,000 nuclei approximately. Here, the red ones split asymmetrically. The blue ones split symmetrically. This is the actinide region. The uranium is here, the plutonium is here. And we knew that as you go down, we get into a symmetric region. We knew that. But as you go further down, you see off here the neutron poor region. There's predicted to be another asymmetric region. This was a bit of a surprise to people. But in fact, at the same time, data came out you can't see, this is mercury 180, which is measured to be asymmetric. So indeed, there seems to be an asymmetric region here as well. Here's an extended version of that. So this rectangle was what I just showed, going up to the super heavies. And you can see again here, it's predicted that there should be symmetric splits and asymmetric splits and so on. So, so this is one thing one can get out of that. And obviously this invites a lot of experimental work to check out whether fission is symmetric or asymmetric. And this in turn tells us a lot about the nuclear structure. So this is potentially powerful information. I just want to show one little thing here about the splits, 4 different regions. The actinide region, this is the heavy fragment and the light fragment. You see the heavy mass tends to be around 10^132. This is why the actinide split asymmetrically, because this one is magic nucleus, is very favored. And then the light one just simply has to adjust as you go to heavier and heavier masses, because it wants to be like for a while. Then it kind of switches over, you see. You see in the super heavy region, that's the red diamonds, you see the same thing with lead 208 playing the role in the doubly magic nucleus. So it's predicted here that one fragment will lie very close to lead, and then the other one will then have to adjust its mass. So as you go up in heavier and heavier systems, the light one becomes heavier and heavier, but the heavy fragment doesn't change at all. So you have a lot of possibility for predicting things in this way. Now, what about other fission observables? There's more to fission than just the mass and charge of the fragments, as I mentioned. There's their momentum, there's the angular momentum, and so on and so forth. Well, this is difficult for the models to deal with, but you can get quite far by analyzing the scission configurations carefully. So I will show you some examples of that. So the scission configuration, here you go through this diffusive evolution, and sooner or later you come to the scission configuration. And here are some actual scission shapes that we have calculated. You see, we stop when the neck is 1.5 Fermi or something here. And then we try to replace these shapes by two what we call proto-fragments. They're kind of drawn in here, makes more clear here. So like this, and like this, and like this. So this is obviously a little bit rough, but this is one way to quantitatively get some scission configurations to analyze. And you can already imagine this scission configuration here, the two fragments are far apart. There will not be as much Coulomb push as up here. So these ones will have lower energy than these up here. Therefore, they must also be hotter, because energy conservation, they're further down on the potentials, they have become hotter. So you can see, you can get a lot out of analyzing these scission configurations. And you can get the kinetic energies, as I just alluded to. I can't see a thing. This has to do with getting how the energy is distributed between the fragments. And the final thing has to do with the angular momenta of the fragments. So I will show examples of these three things here before I finish up. So at scission, we have these two, what we call proto-fragments. They are not the real fragments because they don't have they have strange shapes, right? Each one sits in the Coulomb field of the other. It is distorted relative to its ground state shape. So there is what's called a distortion energy. That's the basically the deformation energy of the nucleus relative to its equilibrium shape. So I'm very sorry about this. It didn't happen before. So there's these proto-fragments, they have a distortion energy, and then they have some internal statistical excitation energy in red here at scission, okay? And then what happens is they move apart due to the Coulomb repulsion between them, and they are accelerated, so they come out with some velocities which we hardly see, and they go back to their equilibrium shapes. So this distortion energy is turned into additional excitation energy. So the total excitation energy is what it was at scission plus what you have gained from the relaxation of the shape. This is important, and you can understand then that if you can somehow measure the excitation energy of the fragments, you can learn something about how distorted they were and how much excitation they had. It's a little bit tricky, but when you couple this to the kinetic energies, you begin to be able to get a handle on it. Let me show that it looks somewhat promising. Here are some results where you do precisely this kind of analysis on the shapes I showed before. And you see here how the kinetic energy, how the kinetic energy as a function of mass matches the data pretty well here in several cases. You also see that it doesn't match so well here for very symmetric splits. And this is probably not the fault of the idea, but the fault of the shape parametrization. It may not, these shapes here like to be very elongated. This is why the table was extended, as I mentioned, but I don't think it has been extended enough. And maybe it's also not true for those that the shapes are spheroids. They may have uplate, octopole deformations, I mean, also. So this is obviously a place where more work is needed. But it seems like one can understand the kinetic energies based on how the scission configurations look. Of course, what I showed was just the mean kinetic energies, but for each and every diffusive evolution, we get one scission configuration and one TKE. So we get a whole distribution of such values for each mass split or the overall one. And let me just show one example here. This is for some fermium isotopes, fermium 256, 258, and 260. And what you see is, here's a typical scission configuration for the 256. It is rather elongated, therefore the kinetic energy is fairly low, and they are relatively highly excited. For the 260, it's the opposite. Here, the scission configuration typically looks like very compact. You get high kinetic energy, distribution centers out here, you get low excitation. So the landscape has different ways you can go. And for this one, it likes to go over a path over a saddle that leads down a valley like this. Over here, it likes better to go this way. And for the fermium 258, it can access both of these values about equally. So you see, you can get some of this, you can get some of that. So it's called bimodal. You can go two different ways for fermium 258, get two different distributions of kinetic energy and other things. So that's interesting, I think. Let's see here, where are we now? It doesn't work, so click here. So this was the kinetic energies. Now the internal excitations, something missing here. Sometimes, as I said, you know, if you get a lot of kinetic energy, there's no energy for the internal, you become cold, and if you move out slowly, you can become hot. But it can also be such that one fragment gets hotter than the other. They don't necessarily share the energy, as you might think. This is kind of curious. You have a total available excitation energy at scission, and some of it goes in the light protofragment, some of it goes in the heavy protofragments. If you look at this and say, well, Let's assume the excitation energy is just simply divided up statistically. Then what you need is the level density for the heavy, the level density for the light, and you can then calculate the probability that so and so much energy goes into the heavy one. Here's examples for two different splits, 106 and 84 here. So nearly symmetric and more asymmetric. And I'll show you two different calculations. One is with a macroscopic level density, the Fermi gas level density that has no shape dependence. And this is the red curve. So it is smooth. And for that one, the heat capacity of a nucleus is just proportional to its mass number. So you can see that the heavy one gets more than the light one just in proportion to its mass. That's where the peak is. You see as you go up in energy, of course, the distribution of energy becomes narrower and narrower and so on. But now the interesting thing is that if you put in microscopic level densities that do depend on the shape, then you have big variations in the level density based on how the level structure is. And in this case here, the nearly symmetric case, the light fragment is favored. And you can see here with the blue that the light fragment gets most of the energy, even though it's the lightest. It's the contrary. And this is because you see here that the light one is deformed. It has a high level density. The heavy one is nearly spherical. It has very low level density. So most of the excitation goes in this one. It's just the opposite here for the asymmetric one, where the heavy one dominates in level density. So it gets most of the excitation energy, and the light one hardly gets anything at all at the low energies. And then, of course, in all cases, as you move up in energy, the structure effects subside and become more and more like the Fermi gas level density. So this is interesting, and this kind of thing gives you information about the structure in these very strangely shaped nuclei. One has some experimental access to that because the hotter the nucleus, the more neutrons it emits. So you can look at the neutron multiplicity as a function of the mass. And here, this has been measured by many different groups, and they get many different results. But more or less common is it goes up and comes down and goes up. It's maybe goes down again and so on. What's called a sawtooth behavior. And what has been put on here is what this calculation I just showed gives in the blue. And you see it reproduces the data fairly well, not perfectly, but the data is not mutually consistent either. But you see here that with the nearly symmetric one here, that was where the light was favored. That's here. So the structure prediction is that there should be extra many neutrons here, and that's true. And for its partner, around 130, there should be extra few. This is around TIM 132, right? And for the very asymmetric one, the prediction was that the light one should have extra few neutrons. You see it comes down, whereas the heavy partner should have extra many, and you see it comes up. So these things are easy to understand then on the basis of the structure of the distorted proto-fragments, not the final fragments, but the fragments you have at scission. Over here, we have how these things, oops, should be one more, let's see here. Hey, well, over here is but I don't know what's going on today. Here is a plot, and you don't see it. It just shows what happens when you go up in energy. And what happens when you go up in energy is that this sawtooth becomes less and less sharp as when you use the saw more and more. And there's data at 5.5 MeV, where it has still some structure left, and the calculation follows very nicely. And then there's a prediction at 14 MeV. There's no data there yet, where it is rather smooth. All right, to the final topic, which is angular momenta. This is a very important topic. These fragments come out typically with quite a bit of angular momentum. And what do we expect? What's the physics of that? Well, here, let me see if this even, this is really bad, but this doesn't work. Well, anyway, the first thing about angular momentum is that the entire fissioning system may carry some angular momentum. If you have spontaneous fission, it doesn't really carry anything. Even if you have neutron-induced fission with thermal neutrons, the angular momentum is so small that it doesn't matter. But there is in principle some overall rotation, but it is not important. And the share of that rotation from each fragment is very little. So this is not where the angular momentum comes from. It comes from the individual rotations of the two fragments somehow. So that's what you need to look at. We see most of it. So there are different kind of what's called normal modes of rotation in such a binary system, because each fragment can rotate, of course. So you have a three-dimensional angular momentum and a three-dimensional. So you have six angular momenta altogether, but they are not independent because you have overall angular momentum conservation, which also is coupled to the relative motion of the fragment. So you have to, so to speak, diagonalize the rotational Hamiltonian, to speak theoretically. And then there are different modes then. One is called a wriggling. You cannot see it, it's called wriggling. And in that mode, the two fragments rotate in the same sense, so, and perpendicular to the fission axis. So you see, rotates like this, and this one also rotates like this. And there's two modes because the X and Y perpendicular to Z. And then there's the other one that's called bending. You can hardly see it. There they rotate in opposite directions, but also perpendicular to the dinuclear axis. So either, let's say, around X or around Y, but like this. And then there's finally the modes where they rotate parallel to the axis. One is called twisting, where they rotate like this, and one is called tilting, where they rotate the same direction. So there are six such modes. They were named a long time ago by Nix and Swiatetsky, and here it says that Moretto used these modes and made a statistical model of angular momentum. He said, okay, let's just assume all the modes are populated statistically. This is quite a reasonable assumption, and then you can calculate how much angular momentum you get. Now here, and you can hardly see it, long time ago with Thomas Dössing, we looked at the development of angular momentum in damped nuclear reactions. Your two nuclei come together, you exchange nucleons, you build up angular momentum inside the nuclei, and we calculated the corresponding characteristic times, the time it takes to build up angular momentum, the equilibration time. You can't see what it says, but it says here that this one is very fast. The wriggling is very fast. And it says that the bending is also fast. So therefore, these are probably important in fission because they will probably be populated. Whereas these two down here, one is slow and the other is very slow. So they may not be agitated very much in fission, and they may be negligible. So this is what we have assumed in our fire code, that the angular momenta are these perpendicular ones for this reason here. So it deviates from this overall statistical model by sort of ignoring these. Anyway, this is what you could expect just on physics grounds for the angular momentum in fission. Let me get to the, so the tentative assumption is that the angular momentum of the fragments tends to be perpendicular to the fission axis, and that those modes are populated statistically. Now, what does that mean then? This is the last thing I will talk about. What does that mean for the correlations between the spins? Because as I said before, you can't look at the spin individually because they're all coupled to each other. So you could somehow think that the spins come out very strongly correlated. This is clear if you agitate, for example, only the wriggling mode. This is the one where the two fragments rotate in the same direction. So like here, the light fragment has the angular momentum here, then the heavy fragment also has angular momentum here. They're totally parallel, completely. If you were to plot the distribution of the opening angle between these two spin directions, you would get a delta function centered at 0, right? So highly correlated spins if you had only wriggling. Similarly, if you had only bending, you will also get equally highly correlated, except they are anti-parallel in bending. There should be an arrow pointing up that's also missing. So you again would get a delta function, but this time at 180 degrees. So it is kind of curious. Each and every mode you populate is highly correlated. Either they are totally parallel or they are totally anti-parallel. However, if you do the calculation and if you populate both of them statistically, then in the end, you get practically uncorrelated spins. And you can see this quantitatively here, the opening angle between the two spins after you populate bending and wriggling statistically is practically constant. It's not a delta function here or here, but it's practically totally independent. So totally independent directions. This may have some observational consequences for the photon-photon correlations. We don't know quite yet, but that's an interesting topic. But keep this in mind, the two spins appear to be approximately independent, one would think, on these physics grounds. Okay, I have used up my time and I will come to the end. Let me see now if my summary slide will work. Not quite. So the physics of nuclear fission, right? And I have talked about some physics because I could not cover everything, of course. Let me summarize. You prepare the system to fission, unless it is spontaneous fission. I didn't speak much of the physics here, pre-equilibrium processes and so on. Then the system evolves, the shape evolves in a diffusive manner, and can lead to many, many different things. I had this ex-udo plurus. There can be so many different, qualitatively different scission configurations. Once you have those, you can analyze them. It would be nice if you can invent theories that can actually calculate, but by analyzing carefully the scission configurations, you can deduce promising results about how fast the fragments will move, how they will rotate, which direction, how much, and how excited they will be in addition to the rotational motion. And then what I didn't speak about is the subsequent fate, the de-excitation, which is sequential, neutrons and photons, and then finally electrons and antineutrinos, and then so on during the delayed processes. So that is about it. And I am now thanking you for your attention, and I'm open for questions. Thank you very much.
Thank you very much, Jorgen. This was a very nice presentation. And yeah, so let's see, there are some questions already in the chat. I guess the first one is from, let's see, Jawar. It's about, actually there are two questions by the same person. Okay, the first one is, can you go to the slide where the yield from 256 and 260 fermium were?
Yeah. Well, there was the kinetic energy, right? There's kinetic energy.
Oh, sorry. No, then they're talking about yield fluctuations. So if you go to a slide where you predicted the yield, the mass yield.
You mean the mass distribution?
Yeah, the mass distribution. Yeah.
But from fermium, I didn't predict from fermium.
Then not that one. Then earlier. Yeah, before that.
Maybe slide 37.
For mass distributions, I didn't know. Yeah, this is a way back. Sorry. Oh,
I guess, I mean, the question was asked around the slide for the
this
Fermi.
was the first mass. This was the first mass distribution I showed.
So I
Was it-
think, oh yeah, so the question was about slide 37, but I think, yeah, so I mean, there are,
37.
yeah, I thought that was the, yeah. And I'll,
Sorry,
no worry.
can't see anything.
The question,
I don't know which one you want to talk
oh,
about.
can you go one more?
Yeah,
One more,
this one maybe. No,
maybe one more still. Yeah, I think, okay, they were talking probably
that's
about, yeah.
what I'm talking about. This is not a mass distribution.
So I think in the, that then would be like a TKE yield. This is the question.
That's what I thought. Yeah.
The question is, these jumps up and down, the fluctuations that there are in the predictions of this.
Aha. Yes.
Are these statistical or are they real fluctuations?
Let me think a little bit, because I didn't do this one myself, but the student we work with did. And let me just think. This kinetic energy, I think they must be statistical, actually. I don't think they are real. I don't think so. Although he did actually calculate quite many events. So why it goes so much up and down, I am not completely sure. But that's a very good question. I cannot answer it, but I can ask him to look into it, because there could also be a grid effect. Because even though, you know, there are 6 million shapes in the table, right? When you come out to scission for one particular mass partition and so on, then there are not that many shapes. And you analyze each one, but then you analyze the next one is a finite, sort of a finite distance away. So, so there could be some kind of discretization effects here, because it seems a little bit systematic, right? Up and down in a very systematic way. It doesn't look random to me. So that's quite a good question. Yes, I don't know. Whoever was interested in this can send me an email and I'll try to get an answer produced.
Okay, perfect. Yeah. The second question, also from the same person, is related to when you were discussing the angular momentum, I believe, when you were talking about the statistical excitation of modes. So populate, like you said, that some modes are populated statistically. And you said, could you please elaborate more on what does it mean to populate statistically?
Yeah.
Modes?
Yes. You have the scission configuration, right? Where you have basically what we call a dinucleus. You have these two so-called proto fragments. Each one has a moment of inertia, and you have in the system a kind of temperature, because you have also statistical excitation of the nuclei. So just think about it as having a temperature, a thermal environment. And then you have these rotational modes, and you know how the statistical population of a mode, of an angular momentum mode, is that the probability for a certain angular momentum is e to the minus s squared over 2 times the moment of inertia times the temperature, right? This is just a Gaussian distribution of angular momenta governed by the temperature, right? The higher the temperature, the wider the Gaussian becomes, and also dependent, of course, on the moment of inertia. So you just pick from such a Gaussian for each of the modes how much it is populated. And then once you have what the mode is populated, then you divide this out for each mode that, you know, the light one gets so much, the heavy one gets so much. That depends on their moment of inertia in that mode, right? Yeah, I don't know if that helps.
I think so. I think that was pretty clear, but let's see if they have a follow-up in the chat. Yep. Okay. That explained it. So
Otherwise, I mean, otherwise, this is described in papers in the literature, so it should not be difficult to find. Otherwise, write me and I can send some references.
so let's see. Those were the.
Yeah, I have a question, Stefano. Jorgen, you didn't really talk about, unless I missed it, the phenomenon of like first chance and second chance fission. Can you speak a little bit about that and how well those phenomena are predicted by the theory?
That's correct. That let me see if I can get to the. I don't know if I should. Where I should. So this has to do with what I call the preparation, right? Where you come in, let us say, you shoot in with a neutron, let us say. Where are we? Oh, close to here now. Here, this is, now we don't see it. Here's the initial nucleus. And then you shoot in with a neutron here, typically, and then you generate reasonably quickly, you generate a compound nucleus. There could be some pre-equilibrium first, but you generate a compound nucleus. But if the neutron has enough energy, then this compound nucleus is so excited that it's very likely emits a neutron before it fissions. Because this fission process is quite slow. This diffusive evolution back and forth and so on takes a long time before you get over the barrier. So there's plenty of time. So if the excitation energy is above the separation energy, then there's a pretty good chance you can emit a neutron. And then, of course, it's no longer the same compound nucleus you have. It's a different nucleus altogether. So if you started with a target of uranium-235, you got perhaps 236, but then you emit a neutron, then you have 235. And then you can emit another neutron. This is what's called, if you go straight through and fission right away, it's called first chance. If you lose a neutron first, it's called second chance fission, and so on. So as I said, I didn't speak about that. This is a matter of competition between neutron emission and fission, the gamma N versus gamma F. Yeah, I didn't speak about this, but you need to take this into account. You need to know gamma N and you need to know gamma F. Or the ratio at least. Was I don't know if this is sufficient to say like
no,
this.
that's great. Thank you.
Jorgen, also they're asking whether it is possible for you to share your email. Maybe one of the things that we're thinking, if you put your email in the slides when we upload them on the website.
Okay, yeah. Otherwise, I don't think I'm difficult to find.
Oh yeah.
I mean, you can go to the LBL homepage and just look me up. There is my email, I think, or you can search on the web. But I'll put it on. But I'm not hiding my email address. So if you just Google it, it probably comes up right away, I would think. But I guess that's a good idea.
This is a tip for everybody in the chat. If you have any questions,
I'm very sorry about this mess with my slides. It didn't happen before, so I don't know what's going on here.
I think it worked out pretty fine. I think that we managed to see the important things. Yeah. I have a question actually. Let's see if, well, depending on how many people are staying on. It looks like we still have 50 people on, so maybe they want to see a bit more discussion.
Right.
My question was, I think, regarding I think one of the most interesting part of this presentation is this discussion of the shapes, the nuclear shapes. And I think when people, maybe like at the undergraduate level, we think about like shapes, we think about like atomic orbitals, like electron orbitals. So is there a connection between the nuclear shape and the atomic orbital shape, like something to do with angular momentum of the single state electron? Or is that like two very different concepts, like the shape of a nucleus and the shape of an atomic orbital?
Yeah, I mean, let's see. I mean, yeah, I tried to emphasize that there is some difference between atoms and nuclei, right? If you start by just thinking about the single particle motion, so that would be the electron orbitals or the nucleonic orbitals. Then, if you have a spherically symmetric potential in the nucleus, and then solve the Schrödinger equation, you get something that is somewhat similar to what if you solve the equation for the electron around a charge. But you don't get exactly the same shape sequence. I think the beginning is rather similar, but the magic numbers change. It's not the same magic numbers. The spin orbit force is quite different in the two cases. In fact, it has even the opposite sign for electrons and for nucleons. And the spin orbit force plays a big role in generating these gaps and so on. Even the level sequence is quite different. But this is now for a sphere. So in the nucleus, the situation is a little different because it's not like a central potential nucleons move around. You have a field, a box or a container of a certain shape that you solve. So if you now change that shape, then of course the orbitals themselves change. And I don't really know how you do this with an atom in the same way. So I don't know if you can somehow discuss so easily how this, let's say, distortion, how this will go with the atoms. But then the important thing, I think, is that the nucleus has a shape, as I explained, because it's built up of nucleons that interact by short-range interactions. But you can't really say in the same way that an atom has a shape. You can always measure its multiple moments, of course, the quadrupole moment, hexadecapole moment, and so on. And you can do that of the nucleus also. So you can always calculate moments, but that's not the same. Just because you have a moment, you don't have a shape in this. There's more in the concept of shape in that, and it's uniform inside, and then there's a boundary. At least this is what I would like to say shape means. Not just that you have something that's not spherically symmetric.
I see. There was a question in the chat that just came in while they were giving an explanation. Is from James. It says on the potential energy mass asymmetry deformation surface. So I believe that's the molar surface.
Right.
It says there are two bands that form. Can you talk about why those arise?
There are two. What forms? What was the last sentence?
There are two bands, like two bands, yeah, like lines, or actually maybe could you go to the slide with the
yeah, so I think you mean valleys or something like this, maybe.
Maybe like yes, some.
This is this way here. Yes, let's see here. Yeah.
I think that's the next slide.
Yeah. Here, first of here, there are two. There's this one and there's that one. This is because you have a, you could go positive and you could go negative, right? So they are kind of physically equivalent. But what you don't see on this one, because it doesn't go out far enough, is there's also a valley here, a symmetric valley. You don't really see it because this thing doesn't go any further.
Actually, I think it's
but I think it comes here. No, I think if it's this one that's being asked about, I don't know.
Yeah, I think that's the one. Yep.
Yeah. So you see, this one lies at symmetry. Right, so you have to go over the high top, you have to go over the high ridge here. This is a symmetric barrier here, and then down. So there is indeed a valley here. So from the energetics point of view, it is not so unfavorable for uranium to split symmetrically, but it doesn't happen. And this is not because it's not favorable, it's because the diffusion doesn't want to go there. It goes around, obviously. What would you do when you're out hiking, right? You would go this way here. It's a lot easier than to crawl up over here.
Mm-hmm.
So it's blocked. It is blocked by this. There's a shell effect here that is positive, and that builds up here this big ridge. So you're deflected around and then you go into the asymmetric valley. There's a possibility later on as you come down, you can go around this way here somehow. So if you try to study how the mass distribution evolves as you increase the energy, then as you go up higher, it's like then this ridge is not so high, but still it is more favorable to go around, but then go around this way, and then you can get in here. And we actually, I didn't have time to, I think I talked about that last year maybe. It's actually very interesting because it turns out, you can imagine to go around here, there's not very much excitation energy just as you go around. So this means you are very sensitive to structure effects in the level density. And because of pairing, there are huge structure effects. And this means as you consider, let's say, the probability for going into the symmetric valley, look at the symmetric yield as a function of the neutron energy, it's not monotonic. It can go up and down because whether you can go in or not depends a lot on this gap in the level density. So this is a very interesting structure effect that kind of is sensitive to pairing in shapes that look like, shapes that look very, very distorted. So from the nuclear physics and the nuclear structure point of view, this is an extremely interesting question about, about this population of the symmetric valley. But this is way too, I think, technical to go into today.
I think this really answers the question very well, but I think they're satisfied. So. I think that was the last question. So,
but maybe could I add just one thing to this? I can't show it here, but I mentioned briefly that there was this very notable experiment by Andreev and others that showed that hydrogen 180, what's called mercury 180 fissions asymmetrically, right? You remember that? And this is very funny. If you look at the corresponding plot, well, first of all, if you look at the energetics, then clearly symmetric split is favored, not asymmetric. Here, asymmetric split is favored, but for mercury 180, the symmetric split is favored. Yet it doesn't fission symmetrically. And this is because, again, there's a ridge in the same way, so it cannot fission symmetrically. But there's no asymmetric valley. It just goes down over here. Not in this way, it's very, very focused, very steep valley, always come out in given way. And this is because of this tin 132. For hydrogen, for mercury 180, it is completely structureless. So you fission asymmetrically in that case, not because you like asymmetry, but because you cannot get to symmetry. So you cannot avoid going asymmetric, but precisely which asymmetry you go to, that's very hard to predict. It's very easy to predict for the actinides because of this shell effect with the tin 132.
Okay, well, thanks, Jorgen, for the great presentation and for taking the time to answer these questions. Thanks to all the attendees for your time and attention and for participating in the discussion. With that, we'll formally adjourn today's session and we will see you all again tomorrow.